So let's learn about moment of inertia. You remember what was the mass. The same role of the mass in rotational motion is given to moment of inertia. Let's start with a warm-up question. I make a bicycle upside down and try to spin this wheel. You know that when you try to spin the wheel, you feel an opposition. What this opposition is for? Hmm? Okay, now it's spinning. Let's say there is no friction. Nothing against the spin of this wheel. Does it have kinetic energy? How can we find it? I don't think it's a half of mv squared. Yes, you are right, my friend. But it might be something similar. How to find the kinetic energy of this spinning wheel? There are too many particles making that wheel, so they might have a kinetic energy, but it doesn't have any translational motion. It shouldn't be a half of mv squared. How to find it? Okay, you remember the brotherhood. We started this chapter with brotherhood. The brotherhood between the linear motion quantities and the rotational motion quantities. For example, the distance has a broader angular distance in rotational motion. Velocity, angular velocity. Acceleration, angular acceleration. Now it's a turn of mass. What's the brother of mass? This is exactly our big question in this chapter. Okay, let me ask you a very fundamental question. What is mass? When I try to accelerate an object, I should apply a force. And let's say the mass of the object is m. According to the Newton's second law, F is equal to ma, okay? If the object is more massive, I feel more opposition. So let's say mass is opposition against acceleration. What do you think about resistance or opposition against rotation? Does it have any kind of rotational inertia? How can we find it? Yes, it does. Let's start from the scratch. Here I have a point mass orbiting a circle. Radius of this orbit is r, mass of the object is m, and the linear speed of the object is v, and it's constant. Okay, also I can consider an angular speed for that like omega, and v is r omega. What is the kinetic energy of this object? Okay, it's a half of mv squared, I know. Then I plug in r omega for v. So it's m times r omega squared. Then it is a half of m r squared omega squared. Then I can pack m r squared and put it here. Now look at the analogy. V is connected to its brother, omega. So m is connected to its brother, mr squared. This is exactly the moment of inertia. Moment of inertia is I. It has a SI unit of kilogram meter square, but keep in mind, in this case, as it's a point mass, I is mr squared. Yes, always I can write the kinetic energy for rotational motion to be a half of I omega squared, and I here is the analog of mass, which is called moment of inertia. But for a point mass, it's just mr squared. What should I do for the other cases? Okay, it depends. I can use mr squared for a single point mass orbiting a circle. But the configuration may be a little bit more complicated. Let's say I have a mass of m1 at a distance of r1 to the center, the other mass m2 of this configuration, r2, and the other m3, r3. I can make a sum and write it as m1 r squared, r1 squared, m2 r2 squared, and so forth. Yes, I can. And in very improved mathematical approach, I should use integration. But I don't want to go over those complicated methods. We will use the results. But a very simplified case also that has exactly the same formula as the point mass is a ring. If I have just a ring, that all the mass of the ring is distributed at the specific distance of r to the center, I can again use mr squared, because I can consider the ring something like that. Let's say there are billions of molecules making this ring. Okay, each molecule has a mass of m1, m2, m3, and so forth. Okay, if I make that sum, I is m1 r squared plus m2 r squared plus, and if I factorize it, I can write it like I equals m1 plus m2 plus times r squared. And this is exactly the total mass of the ring. So I can use it, yes, for the ring, yes. But in general, there are different shapes. They may be very complicated and totally irregular, like this. For the cases like that practically in the high school questions, they will give you the moment of inertia. But in some very easy geometrical shapes, like maybe a sphere, when it's rotating around its axis, it's 2 over 5 m r squared. R is the radius of the sphere and m is the mass. For a cylinder or a disk rotating around its axis, it is a half of m r squared. R is the radius of this disk and m is the mass. The other could be a rod. When it's rotating around its center, it's a 1/12 of ml squared. L is the length of this rod and m is mass. And finally, you can rotate the same rod around one of its ends, like this point. In this case, it's 1/3 of ml squared. But in the other cases, you have hundreds of regular shapes. Using integration, you can easily find the I. Otherwise, it's given to you. Don't worry. Let's go over this question. A bicycle wheel has a mass of 850 grams and a radius of 34 centimeters. Estimate the moment of inertia of the wheel about the axis of rotation. Assume that all the wheel's mass is concentrated in the rim. So the spokes have no mass. Forget about it. The I is very easily mr squared, the case of the ring. So let's use it like this. And the only thing is conversion of the units to SI. 850 must be converted to SI, to kilogram. So it's 0.85. And 34 centimeter will be 0.34 meter. And of course, raised to the power of 2. And finally, the answer could be 0.098 kilogram meter square in SI. This is the moment of inertia of this specific case, this rim. Another question. A uniform disk of mass 0.25 kilogram and radius 0.15 meter rotates about the central axis with an initial angular velocity of this. Calculate the initial rotational kinetic energy of the disk. Okay, when they say initial angular velocity is this, so I have omega initial. And if I'm looking for the kinetic energy at the beginning, so it's kinetic energy, initial kinetic energy to be a half of I omega initial square. Okay, so let's forget about the index of I and then use the formula in a simple way, a half of I omega square. But the problem is I don't know the I. First, I should find this I. How to find it? This is a disk, and you remember for a disk I had a formula of a half of mr squared. So let's use this formula. Mass of the disk is given. Fortunately, it's in SI. Radius also given 0.15. It's also in SI. So I plug in the values and find the I in SI. Then I can use this I in this formula. And then I apply omega 10. Then I make the calculation and find the answer as 0.14 joules. This is the kinetic energy of this disk. If you keep everything the same, but instead of disk you have a sphere. Okay, about the sphere, the only thing that may change is I. So it's maybe 2/5 of m r square. That's all. Regarding the shape, regarding the configuration of the object, you will opt for the relevant formula. That's not very challenging. Two circular disks are cut from the same uniform metal plate. Think about this first statement. We have a sheet of metal with its specific thickness, and then I cut two disks. If I remove them from this metal sheet, they will have the same thickness, okay, because they are cut from the same thing. So thicknesses are the same, just the size of the disks are different, okay? Keep in mind. The moment of inertia of the first disk about its central axis is I. The radius, so one of them is I. The radius of the second disk is twice the radius of the first disk. So here, if the radius of this is r, the radius of this one is 2r. Calculate in terms of I the moment of inertia of the second disk. Okay. About the disk, guys, you know, I is a half of m r square. Okay. Second disk will have double of radius. Okay. What about the mass? Think about it. Okay. Think about a disk like this. A disk is like a cylinder. It has a radius of r and a thickness of d. The second disk, double of radius, but same thickness. Second disk has the same thickness because they are cut from the same metal sheet. So it's d also. Okay? You know that mass is density times volume, because density is mass divided by volume. And so its density times volume of a disk is the area of the disk A times thickness D, because it's like a cylinder. A times D. Okay? D is the same. They are cut from the same metal sheet. And rho, same material. Just A is different. And you remember, area of a circle is pi r square. If I double the radius, I will quadruple the area. So the area of this, the second disk, is 4a. And because of that, mass also is 4m. Because the volume is 4 times of the other. Good. In this way, I got the point. This disk is r, I is a half of mr square. So I write it like I2 over I1 is M2 over M1 times R2 over R1 to the power of 2. I know R2 is 2R1. So this is 2 and it's raised to the power of 2 is 4. About the mass, I told you mass is rho AD. D is the same thickness, rho is the same, but area is quadrupled when the radius is doubled. So I believe that mass of the second disk will be quadruple of the other. So M2 over M1 is 4. R2 over R1 also 2 to the power of 2 again is 4. So the answer will be 16. The moment of inertia of the second disk is 16 times larger. Go over this question again. It's a very important question and a little bit related to geometry. Okay, this is all about the moment of inertia. It will have very important applications in future for understanding the rigid body mechanics. So kindly please take your notes from this lesson and have a review. Thank you for being with me and thank you for your attention. See you.